All right, everybody. If you're not in this room, I guess I would appreciate you coming back. We're going to start the talks again. And I apologize for the false alarm. Before the break, I said 1 hour. I misspoke. It's actually an hour and a half. But I only had a couple people ask me about that, so it seems that didn't matter that much. So I hope the food was good. Shout out to our catering service, Starka Teams. It's the same as last year. We got compliments on it, so hopefully we made the right decision going with them again. We should be live on the stream, so just like before, if you have any questions and you're not here in the theater, then go ahead and chat them on IRC or on the YouTube chat or even to Twitter. And then if you are here, just raise your hand and we'll get a mic to you. So on stage, I have Amaury. Did I pronounce it correctly?
Yeah.
Yes, D points. Cool. I'm going to talk to you all about cryptography, so take it away.
Hey, so I am Amaury. I work in the cryptocurrency space, and because of that, I had to up my game in cryptography, and I've been running various experiments and building crypto in D. So this is what I want to talk to you about. One of the main motivators for this speech is that when you ask about implementing crypto from experts, the usual response you get is do not roll your own crypto. And if overall this is a good advice, this is not very effective because if to begin with you don't know and people just answer you don't do it, then no, do you become an expert? That's a very bad pipeline. And the other reason is like people don't realize why it's difficult and the kind of thing they should and shouldn't do, so they end up doing it anyway and doing it wrong. So what I want to give you here is like examples of how you can build cryptography, the different aspects of it you want to be careful about. Especially on the implementation side of things. I'm not a mathematician, so as far as the mathematical aspect of it goes, I'm just, trusting whatever the mathematicians tells me. But on the implementation side of it, there is a ton of small details you want to be careful about, and you want it to be fast, you want it to be secure. So this is what I'm gonna talk about. To begin with, a quick definition of cryptography so we understand ourselves. If we look at Wikipedia, or actually most definition of cryptography, it mentioned that this is the practice of various techniques where you can communicate messages when there are adversaries. This, I think, is a bad definition because it doesn't cover many things that we usually call cryptography, such as digital signatures. So this is not a very good definition. So I propose another definition where you have people exchanging messages and they want their message to be confidential, meaning that not anybody can read them, only the people that the message is intended to can read it. They want authenticity, so they want to make sure that the message is really coming from who they think it's coming from, and they want integrity, which means that the message has not been tampered with. All good cryptography story start with two persons. It's usual in the field to call them Alice and Bob, and they want to exchange some message. But we are at DConf today, so I think it's more appropriate to tweak that a bit to suit our audience. So we have Andre and Walter, and they want to exchange some messages, and they want these messages to be confidential. Walter wants to make sure that the message really comes from Andre, and Andre wants to make sure that it's really sending the message to Walter, and they don't want any third party to tamper with the message. So essentially, those are the three characteristics. We want to ensure. Those are the different threat model we're gonna have. So the first one is like they want the message to be confidential. So they don't want someone, some evil third party, obviously, to get the message and read it and then pass it forward, and they won't even know about it, but suddenly their message is not secret anymore. Another thing that they can do is like a third party can pretend that it's someone that is not, and because it's electronic communication, then you won't know about it unless you put something specific in place. And the third stuff is like you may want to make sure that the message has not been changed. This is important to differentiate that from the other stuff, because there are different attacks that exist where you can modify a message even though you cannot read it. And as such is like a different category of threat, right? Like maybe here our evil person cannot read what is in the blue message, but is still able to modify it in some way, and Walter is not going to be aware that the message has been modified. All right. There are two kinds of cryptography, mainly. All the techniques, they fall in those two buckets. One is symmetric cryptography. So in symmetric cryptography, the different participants in the system, they share a secret, and they're going to use that secret to ensure the property we have talked about before. And in asymmetric cryptography, they don't need to share a secret. So that's kind of a more powerful techniques, but it's also a bit more complicated. And they are each going to have their own secret, which is called the private key. And they're going to have some public information that is related to the private key that is called the public key, that is not secret, that they can communicate to everybody. And then they can use their private and public key to do various stuffs that we're going to talk about. One very important aspect is like information wants to be free. And this is something that is talked about a lot when we talk about peer-to-peer piracy, for instance. People working in the media industry, they spend millions and millions to try to prevent it, and it's just like absolutely useless. It just doesn't work. And there is this natural phenomenon that when there is an information somewhere, it just wants to leak out. Even if you don't leak directly the information, you leak like way too much information about it, and you can deduce what's going on. An example I put here is like someone phone a clinic that does a paternity test and then phone a divorce lawyer, right? Like you don't know what has been said during this conversation, but you can still, figure out what happened. And this is why when your government say, oh, we're not listening to you, we are just collecting metadata, you want to think about that. Because they do, but that doesn't change anything. You have the same aspect in cryptography, right? So even though you may not leak your key, you may leak some information about your key, and if you leak sufficiently many information, then an attacker can deduce what your key was. And if you're not very, very careful, this is going to happen in all kinds of ways. So to begin with, you want your key to be very, very small as possible. The smaller it is, the easier it is to keep it secret. You want your key to be maximally entropic. That means that if your key is a certain size, you want all the values for a key of this size to be equally probable, or as much as possible equally probable. So you have as much information within that small key as possible, so it's as hard as possible to guess what the key is. And you want the key to be reusable, because if you need to create a new key all the time, then you don't have like one secret, you have like many, many secrets, and it's much harder to keep many secrets secret than just one. So there is a corollary here. Everything that is secret is your key, pretty much by definition. That means that if you use some secret algorithm because you think that maybe it's not a public algorithm, so an attacker is going to have a harder time to figure out what's going on here, you may consider your algorithm actually as part of the key. And that makes your key bigger, so in some respect that makes you less secure. So you're better off using public algorithm that has been peer-reviewed. Another aspect of that is that it's a well-known saying in cryptography that anybody, like even the biggest expert, can build systems that they think are secure but actually are not. So you want to have as many eyes on it as possible, think as many attack vectors as possible. So let's talk about the 3 points we have discussed before and how we can ensure those using symmetric cryptography first. So a quick sum up, this is like the scenario we're interested in right now. So we want to avoid someone from messing up with a message and transmit a modified message. And if someone is doing that, you want to know about it, basically. So the tool to ensure that is hash function. But not any hash function, it's a cryptographic hash function. So what does that mean? Well, Wikipedia is not very helpful, right? Because it explains what a hash function is. And a cryptographic hash function is just a special hash function that is suitable for cryptography. So thanks, Wikipedia. That was a very interesting definition. So what do we want from our cryptographic hash functions? We want confusion and diffusion. So what does that mean, confusion and diffusion? That means that if you get the result of the hash, it's as hard as possible to deduce anything about the input. So in that sense, you want your hash function to be a one-way function. You want to be able to hash something and get the result, but you want to be pretty much impossible to take the result and come back to the hash, to the input. And diffusion is like your hash is maximally entropic. So essentially, if you modify just one bit in the input, you want roughly on average half the bit in the output to be flipped, on average. That ensures that any slight change is going to be as visible as possible and as amplified as possible. So those characteristics, they bring us two interesting properties for our hash function. One is collision resistance. So collision resistance means that it's very hard to find two inputs that share the same hash. I don't know if you're familiar with it, but there is this famous mathematical problem which is called the anniversary paradox, which states that basically if you bring many people in a room like here today, if you have more than 19 people, you have more chance than not to have 2% that have the same anniversary, which seems counterintuitive because 19 is not that big and there is like many different anniversary that is possible. I don't know how many people are there today, but this is pretty much sure that several of you have the same birthday date. Statistically, that would be very surprising than not. This also applies to hash function. And essentially, that means that if your hash function is as good as it gets, you need 2 power n divided by 2 trial to find the collision. So where n is the number of bits in the hash function. So if you have a function that is 256 bits of security, you get 128 bits of security. Basically, you need on average 128 trials to find a collision. And the second property we have is pre-image. So pre-image is like, it's very hard, given a hash, to find some input that is going to give that hash. And actually, if your hash function is good, it's much harder than finding collision. And it's like, 2 power n minus 1. So a lot of hash functions that we consider broken, like MD5 or SHA-1, we know how to find collision for those functions. We still have no idea how to find pre-image. This is a very, very difficult problem, and most of the hash functions we have are very, very solid in that regard, even the one that we consider not that secure. And that also means we can use smaller hashes when we're interested in pre-image resistance than collision. So that may be an optimization we want to do somewhere, depending on what we care about. Essentially, we can put cryptography into 2 categories. So this is not from me. This is from Daniel Bernstein, that is a very well-known cryptography expert. He introduced the concept of boring crypto a few years back. And what does that mean? That means that you want to have a very large security margin on top of what you're doing, right? So right now, 80 bits of security is considered secure enough for most applications. But is it really 80 bit? Like, is it maybe 75 because there is some optimization you can find in the way you do the search? Is it, like you're not sure and you don't have that much security margin here. So any kind of optimization an attacker can find is going to quickly bring your 80 bits of security from the secure zone to the hackable one. So you want to have a good margin. you want to use 128 bit of security, and you want to use a function like SHA-256 or SHA-3 that are recognized to be very secure for collision pre-image. So how do you use hash function in D? There is an interface that is standard in the D library, and there is a bunch of hash functions that are already provided by the library, and they all follow pretty much this interface. So what that is, you have a start function that initializes the hasher. You have a put function where you can give it data to hash, and you have a finish function where it's going to do whatever it needs to finalize the process and give you the result back. So let's take an example with SHA-256. This is not the implementation from the standard lib. For one reason is because it implements all the SHA function at once, and it's huge. So I made like a simplified version of it. So essentially, you have some internal state that you're going to initialize by constants that are defined in the specification. You have some small buffer in it. This use is going to be obvious in a while. And you have your push and your put and your finish function. So the SHA-256 function is going to accept data as input up to the point it gets 64 bytes of data. And at which point it's going to run some algorithm on the data you provided it and update its internal state according to the data you give it. And as you go, your internal state is modified, and it's become tainted by all the data you've given to the hash function. Most hash functions are args operation. It's add, rotate, and XOR. So those are instructions that are very fast to execute, and as far as cryptographic operation goes, hash functions are actually pretty fast. And then you need a special trick during the last round, because obviously you need 64-byte blocks, right? And there is no guarantee that the input is going to be 64 bytes. You want also the finalization to do various stuff to protect against various attacks. So this is what your put function is going to look like. I skipped a part of it, so it's going to fit on the slide, as it's a lot of bootkeeping, but it's not very interesting to understand what it does. But essentially, it's going to take the input. If the input is larger than 64 bytes, then it's going to process this in chunk until it runs into a situation where it doesn't have a full 64 byte to process, and then it's going to store it in the buffer and reuse that as you give, extra input. The finish function is just going to look at how many bytes you have left in your buffer. If it's pretty much full, then it's going to fill it with some padding, run a round of hash, and then fill it with more padding. If there is enough space in it, it's going to just pad it once. And the most important stuff is that at the end, you're going to put the number of bytes that you have hashed in the function. So this ensures there is a kind of attack for hash function that is called l'extension attack. And all the hash functions tend to be weak against this kind of attack. So that means that if you have a hash of some input, but you may not have the input, right? But you can compute from that the hash of this input with some other data that is appended to it. And this can be used to compute stuff that you're not supposed to be able to compute. So once you have seen that, we see that it creates blocks of 64 bytes and give it to the transform function. So the next step is going to look at what is in the transform function. And what is in the transform function is like a bunch of rotate and XOR that just get the input and mix it up in all over direction, do many rounds, so every bit ends up all over the place and having influence all over the place. And then at the very end, you update the states with the new stuff you've been computing. And that's pretty much it. And then at the end, the state you have after the finished process is going to be your hash. So this ensures integrity. You can provide a cryptographic hash of a message or any kind of message, right? And if you change even just one bit in the message, the hash is going to be completely different. So you're going to see that it's different. You cannot use that technique alone. You need either, in addition, confidentiality or authenticity, right? Because if someone is able to modify the message, then what tells me that this same person is not able to modify the integrity check as well. So you need to make sure that there is a way to detect that. There is also obviously fancier techniques than hashes to detect that. Mainly error correcting code are an interesting one, but there's already so much we can talk about here. So let's go to authenticity. Authenticity is very simple, and we can build upon what we just saw here. So here is the scenario we're interested in. Someone is going to talk to you and pretend to be someone that they are not, right? So the tool you did for that, at least in symmetric cryptography, is going to be hashmax. So it's a hash-based message authentication. So how does that work? You have two hash functions, and you have your secret key and you have your message. All right, so you're going to put your secret key in the hasher, and then you're going to put your message in the hasher, and you're going to get a result that is called hi in this slide. And then you are going to do it again with I. So where are we going to do it twice? The reason is we don't want someone to be appending something to the message and being able to still compute the hashmark. And this prevents, if we are going to do 2 rounds, this prevents this kind of attack. So this is a way for hashmark to protect itself against weak hash function. If you are confident that your hash function is very secure, then you can do just 1 round and you are good, right? But if there is a flaw finding your hash function, then you are not secure anymore. With that, there is some extra margin of security. There is some security flaw that can be found in the hash function, and the hash max remains secure. So this ensures both authenticity and integrity, right? If I transmit that with the message, then if the message is altered, then the hash is going to change, and so my hash max doesn't check out anymore. And if I don't know the secret, then I cannot generate the hash max. So someone is sure that the message is coming from someone that knows the secret. All right, hashmax is in the standard lib. It's very generic. You can combine it with pretty much any hash function that is the standard lib. So just use that. It's good. It's pretty much it. So now this is the big chunk, right? So there is a reason why definition like the one from Wikipedia, they talk about this aspect and this aspect only. It's because this is the most, maybe the most difficult and the one there is the most content. So everything starts with, okay, so this is our, this is our scenario, right? So you don't want someone to read the message. So the basic is the Caesar cipher. So this is like the very first cipher, right? So you're going to choose an amount you're going to shift, and for this amount, you're going to shift each letters in your message by that amount. It's not a very secure cipher, but it's obviously it's the first one, right? So it's subject to attack by frequency. So some letters are more frequent than others in most languages. And that means that if you can analyze the frequency, then you can do the mapping between the encrypted letter and the not encrypted letter. Also, there is only 26 key possible, so it's very, very not secure. There is not a lot of entropy in there. So you have the visionary cipher, which is an extension of that. Instead of using one character to do one shift, you're going to use several of them, and you're going to repeat them to do a different shift by letters. So it solves the entropy problem because you can use a very large key, but it doesn't solve the statistical analysis problem. So it's still not that secure. What you want is a stream cipher. So what is a stream cipher? A stream cipher uses a pseudo-random number generator with 2 letters inversed. And so this number generator is going to be, instead of using your key directly to encode your message, you're going to feed your key to a pseudo-random number generator that's going to generate a bunch of random numbers, And so you can have a key that is as long as you want to encrypt the whole message, right? So once you have this key that is as long as the message, you can XOR it with the message. Because the key is completely random, the message now is looking something like completely random, and you cannot do anything with it. So you have very good confusion and very good diffusion, as long as your PRNG has very good confusion and diffusion. And then you are going to use an initialization vector. Why is that? You want to be able to reuse your secret. And if you don't use an initialization vector, your secret is going to generate always the same stream of random numbers. That means that if I know an encrypted message and the decrypted message, then I can decrypt all the other messages you're sending, even the one that I'm not supposed to decode, right? So if you put an initialization vector in addition in there, you can generate a new stream of random number, and you're good. The initialization vector doesn't even need to be private. It can be public, and that works fine. So as we see, we need confusion and diffusion. So we talked about a tool previously that have very good confusion and diffusion. Those are the hash functions, so you can do that with the hash function. And the way you would do it is like this, roughly. So you have a secret key. You have an initialization vector, and you have a position in the stream where you want to generate. And you're going to just hash that, and it's going to give you some random-looking bytes that you can use to XOR with your message. Obviously, this is going to be slower than it needs to be, and maybe if you use the wrong hash function or whatever, this is not going to be as secure as you want. So you may want to use a stream cipher that already exists, and the one that is like the most used right now is chet 20. And it's a good one, so if you want to use that, then just use that. The second tool you can use is block cipher. So block cipher is not a cipher per se, it's a building block to build ciphers, right? So basically the idea is that you have a block, you give it plain text, it gives you a cipher text, and the cipher text is going to be scrambled in a way that depends on the key. And everything it does is reversible, right? So you have a block cipher decryption box that corresponds to the encryption one that can do everything in reverse and go from the cipher text to the plain text. So do you build this thing? Well, first, what do you do with this thing? You can do a stream cipher, right? So you just give it an initialization vector and a counter, and you give it the key, and it's going to give you, things to XOR with. And you increment the counter, and you get more random-looking data. So it's kind of the same technique as the hash function presented before, just with a different tool, and it works the same. There is very common stuff. This is very insecure, and I mentioned it because a lot of libraries are using that by default. So if your library is doing it, just pay attention. If you build some library, just maybe just don't even include that, so people are not going to use it. Essentially, you put the plain text, you put the cipher text, it's going to be encoded by the key, right? And the problem with that is that if you have repetition in your plain text, you're going to have repetition in the cipher text, and it's very visible. And there is a very visual, very famous example of this, where someone encrypted the Tux Pingui. And as you see, if you use ACB, then the Pingui is scrambled, right? But area that look the same on the picture look the same on the scrambled data, right? Like, so all the white stuff just look like these rays, and the black stuff still look blacks, right? So you're leaking a lot of information there. Even though you don't have the original because you don't have the key, you're leaking a whole lot of information. And you want the random looking pattern that is on the right. So the most common way to use it is just by chaining them that way. And it has an advantage compared to stream cipher, is that if you encode different data, even if you reuse IV, only the prefix that is common between your two streams that you are encoding is gonna be, is gonna be able to leak, right? If you reuse an IV with stream cipher, then you're not secure at all. If you reuse an IV here, it's still bad, but it's better. You don't leak the whole message; you're just leaking the common prefix. The most well-known block cipher right now is AES, which stands for Advanced Encryption Standard, and roughly this is how it works. So it has S boxes, what we call S boxes, So essentially, those are lookup tables, right? So you have for each 8 bits blocks of the input, it's going to map 8 bits output that is completely different. So this already creates some confusion and diffusion, right? Because you change 1 bit on the input, after the X box, you have possibly changed 8 bits. So you multiply by 8 your diffusion. You also increase confusion because the output is not correlated to the input in any way. So it's very, unless you know that table, right, it's not possible to go backward. And then you have the P box. So what the P box are doing, they are in between the S box, and they are just scrambling the old bits around, right? So when you do several rounds, you end up with, your S box. Your S box are gonna output 8 bits, and those 8 bits are gonna end up in 8 different S box after the fact, right? So after 2 rounds, each bits of the input are possibility flipped 64 bits of the output, right? So you do several rounds like that, and you just scramble everything in a way that is completely unrecognizable. And between each round, you just XOR with some data that is computed from the key. So if you use a different key, you're going to get a completely different result. As you may notice, shuffling bits around is completely revertible. You can do the shuffling in the other way around. And the S-box is like a lookup table, and you can do the lookup table the other way around. So those 2 operations are completely reversible. So if you have the key, you can do the whole process the other way around and decrypt the stuff. So implementation, how do you implement that? Well, the key expansion and the P-box are relatively straightforward to implement. The naive way to implement the X-box is a lookup table, and this is absolutely not secure, so don't do that. There is actually a very concrete example where people were able to, in milliseconds, extract the private key from IS cipher in the Linux kernel that were used for encrypting your partition without any special privilege or anything. So why is that? Well, it is because if you have a lookup table, then you can measure the timing in the cache after the fact to know what part of the lookup table have been accessed and what part haven't been accessed. And this is exactly what they did, right? And looking, which part of the cache was used and which part of the cache was not used, they could make deduction on the key, and if they're running several times, then they get enough information to figure out what the key is. So that's a pretty serious stuff. And this is where we get into side channel. So this is a side channel. This is the metadata that your government is looking after. So I presented one side channel here that is the cache. Does anyone has any idea what kind of other side channel do exist? Yeah? So you can measure the electric usage, and that's true, and that's a bit out of the scope here because you cannot really do that in software. But if you have physical access to the hardware, you can indeed do that, and people actually do that in the wild. What is there? Yeah? Yeah, go ahead. I may repeat, you don't need to run, I'm going to repeat.
Yeah. Timing?
Yeah, so timing is a big one. If you branch somewhere in your algorithm, depending on some secret, then the different branch may take different time to execute, and by measuring that, you know what branch have been taken, and then you can deduce information on the secret. There is a third one that is somewhat related to that. Does someone have an idea? Or? Okay, maybe not. So the one that is related to that is the branch predictor, right? So even if you manage to make your algorithm in such a way that the 2 branches take the exact same time to execute, so you have no timing leaking, you still have some information about the key that is now in your branch predictor, and someone can extract that information. So the first advice is going to be no data flow from secret to load address. So if you have some secret and you load some data, for instance, in the lookup table, you don't want the index to be dependent on the secret. And the way you do that is like either you don't use lookup tables, or you just get everything in the lookup tables and you discard everything that you don't need. So the way you would do it for AES is actually the S-box are not generated randomly, they are generated with Galois field. So what is Galois field? Well, first we need to talk about prime field, and prime field is just a field on which you do operation modulo prime number, usually a very large prime number in cryptography. So there is nothing very complicated or specific about it. Everybody knows modulo, so this is what you're using, except maybe for division. So you cannot do division on those fields, but you can find multiplicative inverse. So you can find for each number x, except 0, you can find a number such as this number times x equals 1. And this is called the multiplicative inverse. And actually, division is like multiplying by the multiplicative inverse. All right, so now Galois field. Galois field is like the next level, where you have a prime field. You have a set of prime field, a set of n prime fields. And you can do operation on those. So it may sound complicated, but there is actually, like most people that have done some math lesson here, they know one of those. Those are complex numbers, right? This is how they work. So if you want to add or subtract, each element you're gonna add and subtract, each corresponding element. So you have the example, AB plus CD equal A plus C plus and B plus D. Right? And it's a bit more complicated for multiplication because you end up with more elements than you have in your field. So you need a way to reduce that. And to reduce that, we call you use what cryptographers call irreducible polynomial. So it's a bit out of the scope here to describe what it is, but let's say it's just a polynomial for each. This stuff works. And so, for instance, if we consider a squared plus 1 as a polynomial here, that means that for each one in the third bucket, the A times C bucket, you're gonna subtract 1 on the right-hand bucket, and you're not gonna do anything in the middle because there is no x parameter. I choose this one because this is exactly what complex numbers are doing, right? So if you multiply two complex numbers, you're gonna have the expansion that you see here, exactly. So that's how that works. Obviously, there is a very interesting prime you want to use for Galois field. Anybody has a guess for what this prime may be? So there is a prime number that is very interesting for computers for Galois fields. Yes. No, it's gonna be 2 actually, because if you do your Galois field with the number 2, then addition and subtraction are just XOR, because each digit, each element in your Galois field is going to be 0 or 1, and that's it. And so you end up with just XOR. And for the multiplication, then you can do actually there is instruction on x86 to do those. It's not that complicated. So IAS use 2 power 8 Galois field for its S box, and use some given polynomial. So from that, you can compute the value from the S box. And this is what you should do if you implement that stuff. So this is very frustrating. You could do just a lookup table, but if you want to be secure, this is the way you're going to do it. Alternatively, there is hardware implementation in modern Intel CPU, so you may want to use that if you have a modern Intel CPU. That's going to make everything both fast and secure. So it's tricky to get where, as we see, because of side channels. You need to have no load address that depend on the key, and you need to have no branches that depend on the key. And if you want to, use some cipher to make something confidential, then use chat-20 or AES, and don't use AES in ECB mode, and you're going to be fine. All right. The last symmetric cryptographic tool we want to describe are commitment, and commitment are very simple. This is like, what if I want to push confidentiality to the extreme, right? Like, what if I want to not share any information with you? I just want to make sure that you know I have this information and I cannot change it later. But I'm not sharing the message with you, right? It cannot be a simple hash, right? Because say this information is like a vote or something, right? There is only 2 options. Or even a password. A password, like people are going to choose 1, 2, 3, or their family name or some stupid stuff like that more often than not. So there is not a lot of entropy in there. right? So you can just brute force the hash and find whatever was hashed. So you use a blinding factor. So you're going to generate a random number, and you're going to hash the information you're interested in with the random number, which is the blinding factor. And then you can publish this as a commitment, and you can prove that you have this commitment later, and if you need to, by publishing the information on the blinding factor. If you manage any password anywhere in your system, this is what you want to do. You want to hash the password, and you want to add what we call a salt in the password, which is a blinding factor in cryptographic terms. And that means that you're not keeping any information about the password that people are using, and that means that even if you get pirated or something, then any hacker won't have any information about the password of your users. So that's good, do that. All right, let's talk a bit about asymmetric crypto. It's going to be shorter. It's going to be more math as well. So asymmetric crypto rely on math problems that are easy in one direction and hard in another. One people are familiar about is prime factorization. So it's easy to multiply two numbers for a computer, even two very, very large numbers. But it's extremely difficult to find the prime factorization of that multiplication, right? So this is a problem. Another one that is actually more used nowadays in modern crypto than prime number factorization is elliptic curve. So the good aspect of it is that you don't need to share any secret, and that's what you want, right? So what are elliptic curves? Elliptic curves, they are actually a mathematical curve that correspond to this formula, and you can define on it, I'm not going to dig into that aspect too much, but you can define on it a way to add points together, right? And because you can add points together or add points to themselves, then you can define a multiplication between a scalar, which is a number in mathematical term, and a point, like essentially like p plus p equal 2p, right? And p plus p equals 3p, and so on. So you can multiply an integer by a point on the curve and get a result. And the interesting property here is that it's very easy to multiply a point by a scalar, but it's extremely difficult from the result of the multiplication to find out, by how many you multiply the point. So it's a mathematical problem that is easy in one direction and is very hard in the other direction, so we can use that to make for asymmetric cryptography. So the elliptic curve we're going to use is CP256K1, because cryptographers like names that you can understand. The parameter A is 0, which is nice because we can do a lot of optimization because basically the x term is just disappearing. B is 9. It's defined over a prime field that is very close to a power of 2, which is nice because it helps us to do various optimizations. So essentially, like if you were to draw that curve, it's a nice curve, right? But once you define it on the prime field, it just looks like a scattered point on a graph, and there is no pattern in there, and there is no meaningful information you can extract out of that. All right, and then we choose a point P that has point G that has nothing particular on the curve, that is called the generator. So G for generator. And this is just a parameter we agree upon. We have just chosen one point that have nothing specific. And all of that is specified in some document, whatever, right? And with the elliptic curve, we're going to use scalars. And same, they are defined over a finite field that is over another number that is not that quite close to a power of 2. That is pretty close, but not close enough so we can optimize that much. And this number has the particularity that this is how many points there is on the curve defined on the prime field, right? So you can multiply G by any number in there, and you're going to get a new point on the curve. And if you go over that, then it's going to loop because there is only a finite number of points on the curve, right? So you need large integer operations. So one of the problems I ran into when implementing those stuff is that none of the compiler implements cent and usent. And because of that, I ended up using SDC because it implemented cent and usent, and this was a good opportunity to battle test it. I also submitted a fair amount of patch to LLVM to improve the code gen for this kind of stuff. So essentially, that's the kind of code this would like to add large integer in chunk of 64 bits, using usent. That makes everything much easier. Obviously, there is no usent on the machine, but the machine knows to legalize that very, very nicely and generate nice code gen, right? And you have this select function that is very useful because you want to select between two numbers without any branching on the secret, right? So if your condition depends on the secret, you may want to use that. And so you compute like each branch, and then you select the one you're interested in. All right, and this is how you compare, and this is where you see that I'm actually diligent in what I do because I haven't benchmarked that. So there is 2 versions in there. I want to know which one is best, but I haven't got around. Essentially, this is the same stuff, right? It would be very tempting to say, well, if the first digit, one of them is bigger than the other, then okay, this is done. I don't need to compare the other digit. This is over, right? Like one is obviously bigger than the other. But this would leak, private information. So you want to compare all of them, and you use like this kind of algorithm to do it. All right. So no secret, no control flow depending on secret, no secret dependent addresses, so you don't load anything that depends on the secret. And you don't want any bound checks, right? And it may seem counterintuitive because we are doing security code, right? But on those part of code that handle the secret, you don't want any bound checks because bound checks are branches, and you're going to branch on the secret there, right? So you're going to leak information about your secret. So, right, this is like one of those very specific areas. You also want to do that in some native languages. So this is why people keep writing those libraries in C, even though they do buffer overflow and all of that. It's because you kind of have to, because otherwise you're going to have side channel that you cannot control. But you can do it in D as well, and this is this is what is done. It's much nicer than C. Okay. So how do you represent the field elements there? So one of the problems with the scalar element, you see if you do an addition, for instance, is that every iteration of the loop for addition is going to depend on the result of the previous one, right? Because you need to propagate the carry around. So there is 0 instruction level parallelism in there. It's, it's kind of slow. Whereas if your prime number is very close to a power of 2, then you can pull off nice trick. And the way it's done in my specific example is like you're going to have 1 48-bit digit and 4 52-bit digits. So it's bigger in memory, but you can just accumulate the carry in each of the digits, and once in a while you normalize to propagate the carry. You don't need to propagate them all the time. And the benefit you get out of that is that you get very nice instruction level parallelism. So this is what it gets. This is what it looks like for normalization. So this is, you have 0 instruction level parallelism there. You just have the complement of your prime number that is a very small number because it's very close to a power of 2, and you just propagate the carries, right? And what you get out of it is like something like an add. You can do it member by member without depending on anything before, and you need to keep track of how many carry at most you accumulated, so you know that once in a while you need to normalize. The good thing is you don't count actually how many carry you have. You count how many carry at worst do you get, right? So it doesn't depend on the secret. You're going to have some branching on there, but it doesn't depend on the secret. It depends on the algorithm you're using. All right. So do you do point multiplication? For G, G is a parameter of the curve. So for this one, you can do very easy pre-computation. And so you can compute the multiplication for, a bunch of part of the number, and with a few addition, you recompose the results. You can use various techniques to make the lookup table, the result in them meaningless independently. And you want to access every element in the lookup table because if not, then you're leaking information. For other point on the curve, there is a more involved technique that I'm gonna describe quickly. But before, what can you do to blind? So what can you do? You use a point H. And this point H, you don't know any relation between H and G. And you can get it, for instance, by hashing G. And you're gonna add various number of h to all the elements in the tables, and the last one you are going to subtract all of them. And what you get out of that is that any number that is in your lookup table, you don't know the scalar that is associated to this point in your lookup table, right? So any of them, you can look at them and don't get any useful information. Any intermediate state is completely meaningless now, not associated to any scalar that anybody knows. And the second stuff you can do is that you add a number of times g for each row in your lookup tables. And at the end, instead of using your scalar directly, you're going to use your scalar minus b. So essentially, you can use the various value of b completely randomly. So every time you get a different setup, you're going to get different value of b. And as a result, if you end up leaking some information inadvertently, then this information is useless unless you know the value of b. That is runtime dependent. All right. Non-adjacent form. Non-adjacent form is how you're going to multiply those points by an integer if you don't want to do heavy pre-computation on the point. So it's kind of like the Montgomery ladder. So the naive way you would multiply something, following like the manual multiplication you would do on a paper, except the multiplication table is twice as small because we use only odd numbers. And so we do some pre-computation on the scalar, get those odd numbers, and we can do that stuff. So maybe I'm gonna skip over that fast because we're running out of time. But essentially, this is a technique. You can use this technique to multiply any kind of very large integer. So what can you do with that? And then I'm gonna stop. The first stuff you can do with that is elliptic curve Diffie-Hellman. So this is a way to establish a shared secret between two parties without ever exchanging that secret, right? And this was the main problem for all our symmetric cryptography first, right? Like we needed to share this secret between the different parties, but the problem we had, like if we could share a secret securely, why don't we share the message directly securely, right? So we have a problem when sharing this secret. And this is a technique that allows you to come on with a common understanding of what the secret is without actually exchanging it. So Andre and Walter, they're going to choose a secret scalar on their side. And they're going to multiply this scalar by g. And they're going to get a point on the curve with that. And they exchange those points on the curve. And then they're going to multiply the point of the curve of the other guy to get the secret. So at the end, both they compute a times b times g in a different way, right? But nobody knows both a and b. And actually, like Andre knows only A, and Walter knows only B. So those are the only two persons that can compute the secret, and anybody else cannot compute the secret. So now you have a shared secret. You can use AES, you can use, HMAC, you can use like whatever you want. You can do electronic signatures. So electronic signature, you're going to have your private key that is a scalar, your public key that is this scalar times G, and what you're going to do is you're going to hash something, right? And then you're going to do a computation, and you're going to come back to some previous result that is called R here, that you put into the hash. And that is quite a claim, right? Because you put it into the hash, and then you come back to that stuff. So either you broke the hash function, or you know some specific secret. And the specific secret is not that complicated, right? You know that your public key is actually x times g, and nobody else knows that. So because of that, with some simple arithmetic, you can find a way to cancel the value of r. This requires a blind effector that we call k here, and if you leak this k, or if you reuse it, or if you don't choose it very randomly, then you're screwed, because you're going to leak your private key. Because you see S equal K minus E times X, right? And S and E are public numbers, right? So if you leak information about K, you leak information about X. And this is a very concrete stuff, right? Because Sony used that for securing the PlayStation, and they used a bad random number generator for K, and they ended up leaking their private key, right? So there is more fancy signature you can do. And the last thing I want to talk about is homomorphic commitment. So this is quite a nice sounding name, right? But essentially, this is a very interesting idea where you can provide no information about data, but you can provide information about how the data relate to each other. So in this very simple example, Andre wants to prove that it knows two numbers, and the sum of those two numbers is 10. So that's a very, very, very difficult mathematical problem to solve. But obviously, this is kind of like a toy example, right? You can do much more fancy operation there, but that wouldn't fit on the slide. So let's assume that it's very difficult to find two numbers that sum up to 10. And Andres wants to prove that he knows how to do that because he's a real math genius. So it's going to use 2 points G and H, such as we don't know a scalar that from one get to the other. And Andre's node is two numbers, A and B, and he's going to compute A times G plus some random number times H, and the same for B. And what does it do is like it gets two commitments for A and B that give no information about A and B because array and array B are blinding factor. So depending on the value of array or NB, it can be anything. And so Walter can verify that Andres knows his stuff. He knows two numbers that add up to 10 because he can compute 10 times G plus the sum of the blinding factor times H and check out that it corresponds to CA plus CB. And because of that, it doesn't know A and B, but it knows that the sum of A and B is 10. So he knows that Andre knows. All right. I guess that's all I have. A few stuff if people want to ask questions, and a few reminders about how you don't leak. How do you don't leak your private information?
We can take a single question before we go to the break. If there is one.
Hello. So you told us that people are implementing this in C over and over again because it's so easy to control the side channels and stuff.
Yes. Actually, you kind of have to implement it in some system language, not especially C, but you need a system language because you need to be able to control the side channels.
Yes, but let's say given the C as a de facto system language and D, is there any D killer feature that you would like to put a emphasis on while re-implementing that comes very handy and
yes,
a deal breaker?
One of the things that makes it much nicer to do in D is because D has a much richer type system, right? So you can bake plenty of invariant about your code in the type system. So for instance, you can use the type system to encapsulate some information that is supposed to be secret. And if you do any operation that you're not supposed to do with the secret, you can have the type system telling you, hey, no, you cannot do that on this type. This is illegal, right? And because of that, you can have plenty of security that is just checked by the compiler that C compiler would be completely unable to provide for you. Only code review and stuff and praying that nothing slips through.
Thanks, Amaury. Walter, do you mind asking your question during the break? We'll take a quick 7.5-minute break before we get back to the next speaker.
Yep.